The second major idea of fluid dynamics, fluid flow, is Bernoullis equation. This basically just comes from conservation of energy. So you remember, with conservation of energy, we would say that the mass of an object times g times its height at one point, plus 1/2 the mass times the velocity at that same point, would equal the mass of the object times g times the height at a later point, plus 1/2 the mass times the velocity squared at the later point. Well, this was potential energy, this was kinetic energy. With fluids, instead of using masses, we use densities. So you see I've got a rho times v1 squared, a rho times v2 squared, a rho g y1, a rho g y2. But we've added in this extra term here with the pressure. And it turns out that pressure can push us from a low height to an upper height, but we lose some of that pressure in the process. Also, just from dimensional analysis, we remember in looking at pressures as we went down to deeper depths, rho gy was had the same units as pressure. In fact, that showed us the change in pressure from a lower height to a higher height. In fact, Bernoulli's principle can be used to do that, to derive that same equation in the simple case of constant velocity, or the velocity being the same at both places, or zero. Okay, so let's look at some examples for how we use that. Now, we can use Bernoulli's principle to understand why an airplane wing gains lift. We know that it says P bottom plus 1/2 rho V on the bottom squared plus rho G Y on the bottom equals P top plus 1/2 rho V top squared plus rho G Y top. Okay, now let's try and understand this. Y bottom and Y top are slightly different, and as a result of the fact that Y top is a little bit higher, the pressure is going to be a little lower on the top. That pressure difference is basically the buoyant force, and that's how a hot air balloon floats. There's less pressure on the top simply because it's higher than on the bottom, and because it's so light, that buoyant force is enough to lift it up. But in the case of an airplane wing, that difference in height is really quite small. So we can ignore that. However, between the tilt of the wing and the fact that the wing is curved on top, the velocity is much higher on top than it is on the bottom. Okay. This velocity goes up. Well, then if this term goes up, this term has to drop down to keep the whole thing equal. In other words, the faster velocity on top makes the pressure lower on the top, and that higher pressure on the bottom and lower pressure on the top results in lifting the airplane up. Something to note, this net effect does tilt the air downward. So as the airplane flies through the air, it's pushing the air downward. That has to be the case, because if the air is going to push the wing up, we know by Newton's third law, action-reaction, that the wing must also push the air down. So it's not two different principles, but two ways of looking at the same thing happening. A couple other cases that I like to consider, and I'll just talk about them briefly. A baseball, a spinning baseball, effectively has a higher speed on one side than on the other. Okay, so the baseball spins like this. The baseball itself is moving to the right, which means the effective wind velocity is to the left. The wind on the bottom gets tugged by the roughness of the ball, pulled around this way, and and tilted upward. Okay, that means we've got a faster speed here and a low pressure. Whereas on the top, we have a higher pressure. And that will push the ball down. But notice the ball has also grabbed the air and pulled it up. So the ball pushes the air up, the air pushes the ball down, and the ball drops. If it's spinning in a different direction, we get a different kind of curve. Now let's consider a boat. I'm going to look at a top-down view of a boat. So this is a sailboat. And I'm going to draw its sail like this. Now if that sailboat is sailing fairly close to the wind, so wind is blowing this direction, the wind comes around and bends this direction. So I've deflected the wind with a result of getting a force up and left. Now at the same time, there's a small board underneath called a dagger board, or a center board, or a keel, and water flows over the keel the other way, also deflected, giving us a force up and right. But it's the same result of having the air move faster on the outside, slower on the inside, that gives us lift, and the higher pressure at the slow air pushes. The higher pressure at the slow water pushes the centerboard. The net result of these two forces is for the boat to go forward. Surprisingly enough, lift is better than just what's called stall, where you just bounce the wind directly off of the sail, and as a result, a sailboat can actually sail faster slightly into the wind than directly downwind.